Hi, everybody. Welcome to this session. And my name is Anirban Dasgupta. I'm a faculty in computer science at IIT Gandhinagar. And my interests are in basically algorithms as applied to machine learning and data mining. Right? Hopefully, in the span of these 3 sessions, we'll also get to touch upon a little bit about what are the interesting questions that I think are interesting. So this is a little different dynamics than what I'm used to. I'm used to pacing around in the class, but we'll see how it goes. So I've changed the order of the topics a little bit based on what I thought would be sort of a more natural flow. So today in the 2 sessions, we'll talk about clustering first, and then about dimension reduction. Okay. So let's see how it goes. Okay. So clustering, right? So I realized that until this point, you have mostly been learning about the mathematical foundations and the statistical foundations. You have not really come upon what is machine learning yet, right? Have we touched upon the terms what is a supervised learning, what is unsupervised learning? Not yet, not yet. But anybody has any sense of what it is? What is supervised learning?
Classified data to predict like some data as the yes or no, some class labels.
Okay, so let's say in a data set we say that whether a person has a particular disease or not. Okay, so this is the task, is it? So the task is whether to predict that the person is having a disease or not. But what is the input first of all? So the input is some description of the person. Right? It could be a set of medical tests. It could be his or her physiological status, different kinds of things. What else? Is that all? Right. So supervised learning has 2 parts of the input, right? One is a representation of the objects that you're interested in, right? This is a feature representation, typically what we call as a feature representation. And the second is a set of class labels, right? As in, you have to be given a set of people with their labels known. As in, I know that this person does not have cancer, I know that this person has cancer. Now go fit a model, go have fun, right? Unsupervised learning, then what is missing? There are? I'm sorry, I need one person to talk now. You don't have the results. You don't have the labels. We have the feature representation, all fine. We don't have the labels. Give me an example of unsupervised learning. Clustering is not a task. I want a task, specific task. Document what?
The classifying some articles into like science articles, news articles, sports articles.
Good question. Good question. Let me take that. So classifying into an article, into a science article, philosophy article. Is that a supervised or unsupervised?
Supervised.
Could be either.
No, that we have to classify.
Could it be either? It could actually be either, and we'll see that we might see examples of both. We might see examples of one today and the other one later on. Anything else? We have not. I don't yet have a satisfying example of unsupervised learning. Pixel segmentation. What's there? Right. Here I have cast it. You might cast it as an unsupervised problem. Right. I mean, I'm giving you an image. And in general, you know something about what is foreground, what is background, and you're not. So given that image, I mean, you have never been given a label, right? You've never been given a label, but you still want to find out. Okay, can you partition this into interesting place, into interesting zones? Can you segment out an object? Can you segment out what is the foreground, what is the background, and so on, right? So why would you do unsupervised clustering? I mean, why would you do unsupervised learning? Because you're starting off with less data, right? Why is that a good thing? What does it mean? I mean, so in what kind of tasks would you actually go for, or would you be forced to go for unsupervised learning?
Real time.
Huh? Real time? Not necessarily, because in supervised learning, in real time you might only have to do what is known as the classification, the test. I mean, running the model on the data, which is pretty fast typically. So,
It's actually really difficult to label whole data and data sets for taking your model. So in a supervised model, give us an edge so that we can make some better models.
It's a good question. So that's a good point. That in sometimes it might be very hard to actually get a label, right? In a lot of these cases, you might not even have a label. Right? So imagine that suppose you're in a company and a credit card company, and you're trying to detect fraud. I mean, if you knew that these are the fraud cases, right? Then of course it's fairly easy. Then the problem is solved, right? But how do you know that these are the fraud cases, right? I mean, if somebody has and the fraud cases are adapting, right? I mean, if they kind of know that this is the kind of classifications, they're adapting. So you want to detect things that are out of the ordinary. Right? That's all you know. That's all that the problem definition is. That tell me things that are out of the ordinary. I mean, typically classified as anomaly detection, right? And there, really, you have to do unsupervised learning, because what does ordinary mean? I mean, even ordinary does not have a single definition. There is you who probably, do these kinds of spending in credit cards. There's me who probably does this kind of spending. So you really have to get a sense of what are the different types of spendings in which there are a significant number of people doing this kind of spending, and then given all these types, this is still out of the ordinary. Right? So that's clearly an unsupervised problem. And as I've mentioned here, customer shopping results. So let's say you are Google, and you want to sort of create targeting profiles. You want to sort of make sure that everybody sees personalized ads, right? Now again, everybody's preferences are different. What you really sort of look at, what you really search for, is based on so much history that you have. So there, and you cannot really create targeting profiles based on individual people, because that data is too small. So what you do is that you sort of cluster people in saying that that this is one category of people. You might have an interpretation for that category, right? You might have an interpretation that says that, okay, this is the category of mostly housewives, right? Or other category of people who manage houses, right? And then they have certain kinds of things that they need to buy. So that's one cluster, right? And the way that this is done is not through supervised labeling, but through unsupervised clustering, because in most times you don't even need to interpret what the cluster is. You just need to use it. Another big result, and another big sort of direction that doesn't go into machine learning so much, but comes up so often in general algorithms, is optimization, right? In the sense that suppose you have data, right, and you have to distribute this data over multiple machines. Okay, so imagine this data is like the Facebook graph, right? And you want to run some computation, right? But the problem is that whenever you run a computation on a graph, any kind of computation. So what all have you seen? You have what all graph algorithms have you seen? Not just here, before. Give me an example of any graph algorithm. Shortest path, right? Suppose shortest path or minimum spanning tree, right? So then if you cannot really do that if you have one part of the graph, arbitrary part of the graph in a single machine, right? It's very hard to do that, right? Because there will be constant communication needed between these machines. So what you could do potentially is that you could partition the graph, right, into reasonable parts that have little connection among themselves. So let's say you're able to do that. Let's say you're able to partition the graph into pieces that, let's imagine the ideal case, that in the most ideal case have very little connection or even disconnected. Right? That would be a perfect way of parallelizing the Dijkstra or minimum spanning tree or any such computation on these graphs, right? Because then the machines won't have to communicate amongst each other, right? So generalizing this, distributing data across various machines is a big application of clustering, right? Similarly, city planning, facility location, right? As we'll probably mention as you go forward, that one interpretation of k-means is that suppose you have this city, right? And you have the population distributed in this city. Right? So you have some probability distribution that you have created, in which the height of the over the city of Goa, in which, let's say, the density of the probability distribution at any particular point represents how many people are there in this location. Okay. Now you want to say that where should the fire engines be, right? Because if there's more people in a particular location, there's a higher chance that, that there's a fire catching off, and so there needs to be some fire engines nearby, right? So somehow I need to partition my, but let's say I have only 1,000 fire engines. So somehow I need to partition my sort of entire space, right, into, I mean, it cannot just be equal partition grids, right? Because then there might be that there's a big location in which there's nobody really, so I don't really need to put that many fire engines in there, right? So it has to take into account the density of the space. But it's possible to partition it so that, I mean, I can have some kind of guarantee of service, right, in there. And frankly speaking, there's, I mean, the example that we have here at the bottom, okay, I should be using this. Yeah, the example that we have here at the bottom is what is known as a gene microarray. So this green and blue thing that you see, so on one side of it are different kind of genes, right, human genes, I don't remember if they're human genes, but different genes. And on the other side is a microarray. So consider a microarray as a set of experiments that you're performing on the gene. That sort of says that whether at each location of the gene, a particular sort of, so imagine a gene as just a string. And these experiments are saying whether at the ith location of the gene, a particular substring is present or not. Let's say a particular substring is ATTC. Is at that location of the gene, is that substring present or not? And these locations turn green or red depending on the result of the experiment. Now you want to see whether these genes are similar or not, right? Because why do you want to see that? Why would you want to see that, for instance? Whether two genes are similar or not? Because they're going to tell you, huh? That's one. They're also going to tell you about what is known as phylogeny. Right? If you have a gene from a human and a chimpanzee and I don't know, crocodile, right? So two genes that are close to each other in terms of the important regimes are likely to have common ancestor later on in the evolution period, right? Are likely to be closer to each other. So that's one. Okay, so enough this thing. I guess I've convinced you, hopefully. So what is clustering? Clustering, in a very, very broad sense, very 10,000 feet level, is really a grouping of objects into meaningful groups. Okay? Now, this is a very vague definition. You all should be shouting me down. So, how many? What is small? Right? Not clear. So, is it small? Is it constant for all data sets? Can it grow with the number of points as the number of points grows? What is small? What is meaningful? Right? None of this is clear. And we know that there's no supervision, so who's going to tell us about all this? So we need to develop a neat framework, a nice framework of clustering, right? And a large part of what we do now in this first class is going to be in terms of developing this framework. So let's say in this very simple example, right? In this very simple example, we have this. So imagine that these red lines are not there, right? So we have this set of data points, right? All the gray points. Now the question is that do you have? Should I be putting these ones in one cluster and these ones in one cluster, these ones in another cluster, or should I be partitioning these set of points? Should I be using this or should I be using this? Yes, no, votes. Second one, first one. Nobody for the first one. So you're not too polite. Nobody's going to tell me that this question doesn't even make sense to me, right? You should tell me that this question doesn't even make sense to me because you have not defined to me what is meaningful. You have not defined to me that whether it makes sense to partition the first way or the second way, right? So until I define that, this question is meaningless. It could be there. It's like religion. You could choose anything. Okay, so let's see what we need to do in order to make this question concrete. Because we are computer scientists, we want to make this concrete, we want to make this mathematical. So first what we need to do is develop a representation of an object. Okay? So what is an object? You might have seen a representation of an object because in real life, your objects are going to be people, your objects are going to be documents, your objects are going to be images. And is it even clear that they can have the same representation, similar representation? Then, and if I want to run, these mathematical tools that you saw, this LU factorization, QR factorization, they don't work on people, they don't work on images, right? They work on vectors, they work on mathematical things, right? So how do I go from an object to one of these things? Okay, And it turns out that even now that there are many different possibilities that you could use. Right? So the object representation is not necessarily unique. You could potentially use, for instance, you could potentially use a vector representation of an object. You could potentially use a set representation of an object or a sequence representation of an object. And these are only 3 of the most obvious ones that I mentioned. Okay? So let's see examples. So given a document, right? What is a vector representation of a document? So somehow, we are going from a document to a vector representation. So let's say, what is this vector? What is this dimension? What are the elements in the vector?
Unique words are given IDs.
So the document's unique words are given IDs. So one reasonable way of thinking about the document is that a vector representation of a document is that you say that, okay, let's have one dimension for each word, right? Let's have one dimension. D corresponds to number of unique words. Let's talk about documents in English dictionary. Is that always sufficient? No, of course not. If your documents are HTML, you need to include HTML tags probably. If your documents are, bilingual, you need to augment your dictionary, right? If your document is Twitter, you need to include hashtags probably, right? Okay. So I fix the dimension, but how do I go from a document to a vector? What is one possible way of going? Counting keywords. So this is, I won't repeat, so the answers are all very close, that's why I'm not repeating them. This is known as a bag of words representation. Right? In the sense that we are forgetting that we say that, okay, I'll ask you what we are forgetting, right? We say that, that we create a vector corresponding to a document in which the ith term of the vector, let's say we say that, look at the ith word in the English dictionary, count how many times it appears in the document, right? Have that count put that count in the ith term of the vector. Clear? Any question with this representation? What are we losing? The structure, basically, the order, right? In fact, we have taken up the document. We have cut up all the words, and we have sort of put them. Completely forgotten about the order, right? What else could be the problem with this? Which words will have high counts? Stop words, the articles, right? Which are kind of useless, right? So we need to do something more with respect to this document representation. So in fact, this itself is a non-trivial question. That how are you going from a document to its mathematical representation? And you'll find lots of heuristics, lots of different things. However, that is not my concern as of now. I know that somebody has given me the document representation, the vector representation of a document, and that's all I'm concerned with right now. Okay? But you should know that what are the things that come with it. What about a set? Why do I say a document how can I represent a document as a set? The set, so the elements of the set are only the words in the document. So in some sense, you might say that you're losing even more, right? You don't even know that if a particular document talks 10 times about Narendra Modi, you're not even keeping a count 10. You're just saying that the word Narendra Modi, or rather the phrase, appears in this document, right? Oh, just to sort of augment on this, you need not take only single words. Right? Sometimes what is done is that you take sequences of 2 words, 3 words, and so on. Right? So then the dictionary, then the dimension would be the sort of all possible 3 words in the English dictionary. So you're blowing up the dimension by a lot, and we'll see the effect of that. Right? So and then you put in a count saying that if this triplet appears in a consecutive sequence in this document or not. Right? So and similarly for a set representation, you can say that the document is really a collection of, so these are called bigrams. A single word is called a unigram, 2 words is called a bigram, 3 words is called a trigram, and kgram, and so on. And there are other fancy things, skipgrams and so on. So okay, so represent document as a set, big deal. Let's see what happens. Image. How do I go from an image to a vector? Pretty easy. Basically, image, you can think of it as a two-dimensional thing. Just linearize it into a vector and then put in the, what value in that vector? Put in some either some intensity value. If it's a grayscale image, I'll put in some RGB values. Right? Some combination of that. So from a DNA or from a time series, we get a sequence, right? That's yet another mathematical representation. So why am I boring you with this? What we'll see is that I mean, depending on the particular mathematical representation, we need to define what is known as a distance function. We need to define what is known as a and based on this distance function, the complexity. I mean, our algorithms sometimes will change dramatically. So how you represent your data is very crucial in terms of what the complexity of your algorithm is. Sometimes, okay. There is actually yet another representation which actually has a slightly different motivation, right? Because here, for instance, when we were interested in documents, images, DNA, we were only thinking about the objects by themselves, right? We were not thinking about, okay, I mean, are these two documents referring to each other, right? If the document is a blog post, are these two documents referring to each other? Right? Are these two people, if the original data is people, are these two people talking to each other? This is known as the interaction representation. And this is where we need to go from individual, I mean, collection of objects to notions of graphs, hypergraphs, etc., weighted graphs, whatever you want to call, right? And we'll touch upon on some of these. So it could be the graph could be the Facebook, with the nodes to be the set of users and the edges that represent the interactions between them. It could be proteins, where the nodes are the proteins and the edges are where the two proteins interact with each other in any cycle or so, in any chemical cycle or so on. Okay. So now, and once we have the representation, then we need to define what is known as the distance function. What are you going to do with it, right? And here are some examples of distance function, right? We'll go over each of them. So, but there are certain properties it would be nice to have for a distance function to have, right? And some of these properties you already know. These are called metric properties, right? So the first property, dxx equal to 0. What does that mean, really? Distance of a point to itself. So d is the distance function. So imagine d as something like it goes from the set of objects to the set of objects and goes to and gives you a real number. So basically, it tells you that give me two objects, I'll tell you a distance between them. Think of it as a black box, okay? And it obeys symmetry. It would be nice to obey symmetry. It obeys triangle inequality. However, we'll see examples in which these do not happen, right? Furthermore, and this is something that you might not find in any general textbook, but this is something that I like to call that is actually useful in clustering, which is this notion that it should be possible that if you're given a set of points, so imagine these red things are the points, right? And I should be able to find out one point, some object, some representation, such that the sum of these distances is minimized. Okay? So give me an example when the distance is the Euclidean distance. When does this happen? That suppose I'm measuring the straight line distance. Suppose my objects are just points in this two-dimensional plane, and by distance I only mean straight line ruler distance between them. When does this happen? What would be this blue square if it was to minimize the sum of these distances? What does center of the plane mean? Define more clearly. So the answer I'm hearing murmurs is centroid, center of the plane. What does that mean? So define it clearly. By definition, so again, the answer I'm hearing is that the point that is close to all other points. That's by definition. That's what I'm asking. A point that is the sum of distances to everybody else is minimized. So my question is that, suppose these are points are xi, yi. What would be this point? Let us call this point x bar y bar. What is x bar? This point would be the mean of all the points. Precisely, that's what I'm asking for, right? This point would be the mean of all the points. So x bar would be mean of all the xi's, and y bar would be mean of all the yi's. The point I'm trying to make is that this is very crucially connected with the fact that we measure distance according to the straight line distance, which is the Euclidean distance. If I were to change the Euclidean distance, right, and measure it with something else, as we'll see, this does not remain true. This does not remain true. Huh? And in fact, let's say that, so just to sort of push you more, that suppose I say that the distance between 2 points is this. So there are 2 d's, don't mix up between the two. The d on the top is the dimension, the d here mentions the distance function. So this is what is known as, does anybody know what this is called? Manhattan distance, L1 distance, taxicab distance, and so on. So in mathematics, L1 distance. So if this was my distance function, what would be the right definition of x bar and y bar to minimize this? I still want to solve this problem, except that the distance function is this. Does anybody know? That's a fun answer to this. This is not true anymore. What are the measures of centrality, do you know? Median. So in fact, here x bar would be, so this is not easy to prove. Median of xi's, y bar would be median of yi's. This is not easy to prove. I'll give you a task. If you want to prove this, if the points are on the are all on one dimension, right? If the points are in one dimension, and you want to sort of find out, okay, what is the center point? By center means I'll minimize the sum of absolute distance from everybody. This would come out to be the median, not the mean. If we are doing the square, then it's the mean. Okay, so we'll see. So now let's go forward. So let's define some of these norms a little more accurately. Although I'm sure you know some of these, so feel free to tell me. Feel free to sort of say that this is going a little sort of boring. We want to get to more interesting stuff. Let us define the Euclidean or the L2 distance. Right. So x is and y is. Okay, this is a Euclidean or L2 distance. L1 norm we have seen. Any guesses what is LP norm? What would I do? Right. So what we would do is, I think it's okay. The pth power of this. Okay, so I need to be a little careful because p might be odd, so therefore I have to take absolute values and then I have to take pth power and so on. What would be L infinity? L infinity? P goes to infinity? P goes to infinity? So notice that, so why is that? P goes to infinity, I'm claiming how is this in sync with the previous definition? Because in mathematics, you always want some rationale, right? So why do I define LP norm to be like this? And when I plug in p equal to infinity, I suddenly go over to max. Instead of doing trying to follow the above definition. Why do I do that? Are these two definitions connected? So maybe what we are saying, that's a very good point. So let's say that the infinity happens at the first position. That xi minus yi, that difference is maximum at the first position, right? So one way. So what do I need to do? I really need to take p tends to infinity. The limit p tends to infinity. That's what I really want to do, right? And if you think about it a little, I mean, like 2 minutes, if I had given you 2 minutes, it would not have been sort of very hard for you to see that if you take out the maximum of these terms, take that out of the sum, right? Then the terms that are left are all the ratios of the ith term with the maximum, right? And therefore, when I let p tends to infinity, they all go to 0. Because any, I mean, let's say if I'm taking out, let's say x1 minus y1, let's say y1, and then the remaining sum becomes summation over I equal to 1 to p xi minus yi to the power p divided by x1 minus y1 to the power p. So now each of these terms is less than 1 because it's divided by the maximum by definition. And therefore, if I let p tends to infinity, this sum, it's not very hard to show that this would go to, plus there would be 1. So I not equal to 1 plus 1 because the maximum term would be there. So this part would go to 0, and this part would be 1 left, so therefore it would come out to be the maximum. So the maximum gap. So it's all very logical, okay? Is it easy to calculate averages? Not always. I know for L2 it's easy. For L1, I just sort of convinced you by that it's median. I mean, I don't know if you're convinced. It certainly took me a long time to convince me when I saw this. For LP, I don't know. For general P, it's not easy to find an average always. Right? Another distance function that is related to this is what is known as a cosine distance. What is a cosine distance? So for cosine distance, this is what we do. Right? That suppose sometimes we'll have a set of points that are d-dimensional such that the 2 norm is 1. Right? That they're all sort of normalized. They all lie on the surface of what is known as the unit sphere. So this is the unit sphere. So the points lie on the surface of the unit sphere. Right? So a more natural definition of distance sometimes in that case is that we measure the angle between these 2 points. Right? And why is that cosine distance? Why is that called cosine distance? Because it's really cos inverse of x transpose y. I should really divide by norm of x, norm of y, but because norm of x equal to norm of y equal to 1, I don't need to do that. So this is cosine distance. Basically, imagine that the points are all on the surface of a sphere. Take 2 points, measure the angle between them. Right? This is a distance function. Right? So for each of them, it's not obvious that they are distance functions always, that they satisfy dxx equal to 0, of course, dxy equal to dyx. But triangle inequality, that's not always obvious, right? Specifically for the non-intuitive distance functions.